In this video, we discuss an important integrals. Friends, we are familiar with the Riemannian integral. In the previous video, we have seen various theorems on Riemannian integrals. When we integrate some functions, for example, I would like to integrate suppose x square between the limit 0 to 1. Here the function is f of x equal to x square, where x lies in the interval 0 to 1, and you can see that we can obtain value of this function at each point in the interval 0 to 1. Suppose we take another function. Suppose my function is x cube plus 3x plus 5, and I would like to integrate this function from 1 to 10. Then my function is f of x equal to x cube plus 3x plus 5, where x comes from the domain 1 to 10. You can see that whenever we put any value of x from this interval 1 to 10, we can obtain the value of the function f of x, and this function is an easily integrable functions. When if I would like to integrate the function 1 divided by x square between the limit 0 to 1, here the f of x is, my f of x is 1 divided by x square, and value domain of this function is 0 to 1. Then you can see that we do not have we have not defined the function f of x at the point x equal to 0. It is indeterminate at the point x equal to 0. Let us take another type of function. Suppose my function is of the type 1 plus x square, and between the limit minus infinity to plus infinity. Again, we have not defined the function 1 divided by x square at infinity and at lower minus infinity and upper infinity. Another function, if we take x into 1 minus x and between the limit 0 to 1, then this function is not defined at x equal to 0 as well at x is equal to 1. So this type of functions which are integrable, these two examples, you can see that where we can obtain value of the function at each point of the domain. These type of integrals are called as a proper integrals. And this this type of integral where we have singularities, this is not defined at x is equal to 0. So this function has a singularity at point at x is equal to 0. This function has a singularity at infinity, both plus and minus infinity. This function has a singularity at x is equal to 0 and at x is equal to 1. So this type of integrals where the function has a singularity are called as an improper integral. So this is a very important definition to differentiate the integrals, proper integral and improper integral. In the proper integral, we can find the value of the function at every point of the domain, but in improper integral, the function has a singularity at some point, at finite point. Then such a type of integrals are called as an improper integral. So this remember this definition of improper integral. Now we will define how we will see what are the conditions of integration of such a functions. Definition of integration of improper integrals. Let let a function let a function f be defined defined in in an interval in an interval a comma b everywhere everywhere except except possibly at a finite number of points, except possibly at finite number of points. Then convergence at the left end, convergence at a left end. So this is my interval a comma b. You can see that b is right and a is left to me, and therefore a is called as a left end and b is called as a right end, and here this is like this. Okay, so here let us see how if the function has a infinite discontinuity at point a. So here we consider let a be the only point of infinite discontinuity, infinite discontinuity, infinite discontinuity. We are taking this left end as a infinite discontinuity of the function f, like this. This is 1 divided by x square and 0 to 1. Then the function has a singularity at the point 0. So this type of functions. Now in the integral, then the integral, we take the integral a plus lambda to b f dx if exist for every lambda where 0 less than lambda less than b minus a, then the improper integral, then the improper integral, which is that integral a to b f dx, this is an improper integral. At this point the function has infinite discontinuity, is defined as limit of integration a plus lambda to b f dx lambda tends to 0. That is, we have taken integration of f between the limit a to b equal to limit integration a plus lambda to b f dx lambda tends to 0. If this limit is exist, then the improper integral, if this is exist and finite, then the improper integral a is said to be the improper integral f dx between the limit a to b is said to be exist or converge, otherwise it is called as a divergent. Okay, so what is the process to remove the inequality, remove the singularity? At this point we have taken a plus lambda. So look at this, this is my example. Here 1 divided by x square, 0 is the point of infinite discontinuity or singularity point, then we take this as a 0 plus lambda. so that it will be lambda to 1 divided by x square, and you can see that we can obtain the value of this function from lambda to 1 everywhere. Okay, and we have removed the discontinuity of the function by addition of lambda. So such a type of remove when we remove this such a type of singularity and take the limit of this new integral, lambda tends to 0. Evaluate this, take limit lambda tends to 0. If it is exist and finite, then this integral is said to be exist or converges, otherwise it is said to be divergent. So this is the definition of convergence at a left end. Similarly, we can define the convergence at right end. Second, convergence at right end. Convergence at right end. That means at the point B. So only B is the point of let. So let first consider B is the only point of infinite discontinuity. Infinite discontinuity. We are taking this point as an infinite discontinuity point, discontinuity of the function f. Then the improper integral is said to be converge, or it is defined as integral a to b is equal to, here we take mu tends to 0, integration a to b minus mu f dx between the limit f dx where 0 less than mu less than b minus a. If this limit is exist and finite, then we say that the improper integral exists or converge at point B. So remember this, we have removed the singularity of the function at the right end by taking this point mu. For example, if my function 1 minus x, and I would like to integrate this from 0 to 1 between the limit 0 to 1, then you can check that this function has a infinite singularity or discontinuity at point 1. Then in such a case, we take this as a 1 minus mu, and this will be 1 minus x into dx. Now you can see we can obtain the value of the function at the point, at the upper point. Then evaluate this integral and take limit mu tends to 0. If it is exist and if it is finite, then we say that this improper integral converges at the right end, and it is said to be exist. Okay, if it is not happens, if limit is not finite, then it is said to be divergence. So we have seen the discontinuity, convergence of improper integral at right end and at a left end. Now what happens if some functions has infinite discontinuity at the middle point? For example, if say consider the same example, 1 minus x into dx, and if we take the range from 0 to 5, then you can see that 1 is the in point of this interval 0 comma 1, 0 comma 5, and at this point this function has an infinite discontinuity. Then in such a case, for example, if would like to, this function has infinite discontinuity at point at a C, and which is lies between this A and which is lies between A and B. A is less than C less than B. Then we divide this range into two parts, A to C f dx plus integration C to B f dx. Then the first integral have a discontinuity at the right hand, and the second integral has a discontinuity at a left end. If both this integral exist, then the function is said to be convergence, otherwise it is said to be divergence. Okay friends, now if we can extend this to up to finite points. For example, we have a is less than c1 less than c2 dash dash less than cn and less than b. Then these are the finite points at which the function has an infinite discontinuity, we divide this range a to c1 f dx plus c1 to c2 f dx plus c2 c2 integration c2 to c3 f dx plus integration cn to b f dx. Okay, now you can see that the function is also defined as both the end. Suppose this function has a discontinuity at both end, then a and b as both end, integration a to b f dx at both the end, then we write it as limit mu tends to 0, limit lambda tends to 0, integration a plus lambda b minus mu f dx. Then by adding lambda and by subtracting mu from the upper end and addition at the lower end, we can remove the singularity of the function at the end and evaluate this function integral and take the limit with respect to mu and lambda. If it is exist, then the function is said to be convergence at both the ends. And here you can see that if all these integral exist, means this function has a singularity at c1, this function has singularity at both the points c1 and c2. So apply here left definition, convergence at the right end, this for convergence at both end, and this at convergence at the left end. If every integral is exist, then the function is said to be convergent, otherwise it is said to be divergence. So this is about the convergence of the function at interior point C between A and B. So friends, you can I hope you have get the idea how to evaluate this type of integrals when the function has a singularity the at some finite point. Thank you for watching. In the next video we will see some examples. Thanks once again.